Good morning to all. Today we will discuss the acceptance angle determination of an optical fiber. First we'll see what is optical fiber. It is a thin hair-like structure which is made up of a transparent material. It consists of core and cladding, where core glass is surrounded by a cladding material. The cladding is covered by a buffer jacket. Normally it is in color of black. It acts as a protective layer for core as well as cladding. The principle which is used in fiber optic communication is total internal reflection. In order to have a total internal reflection, the three laws should be satisfied. The three instructions conditions are: light should travel from denser medium to rarer medium, and the angle of incidence should be greater than critical angle, and the refractive index of core should be greater than refractive index of cladding, that is n1 should be greater than n2. Now we will discuss the acceptance angle. It is the maximum angle to the axis at which light may enter into the fiber so that it can have total internal reflection inside the fiber. Now we will see the diagram of a material fiber. It consists of core and as well as cladding, where core is appear in white and grey color is cladding, where the refractive index of core and cladding are N1 and N2, and the refractive index of air medium is taken as N0. Fiber accesses the middle point of the core. Now we will discuss the derivation part. Consider a cylindrical fiber with the refractive index of core and cladding are N1 and N2, and also refractive index of air medium is taken as N0. The incident ray travels along OA, that is from outer face to core medium, and enters into the core at an angle of incident angle, that is I. The ray is reflected along OB, that is inside the core, at an angle of theta in the core. If further proceeds to fall at critical angle of incidence, that is psi is equal to 90 minus theta on the interface. At this site, the ray just moves from along BC, that is inside the core. Hence, the angle of incidence is taken, that is psi is equal to 90 minus theta at the interface will be more than the critical angle. Hence, the ray is totally internally reflected. That is, it satisfies the condition number 1. And applying Snell's law at point of OA, that is outer layer to interface, N0 sin I is equal to N1 sin theta. So Ni is equal to N1 by N0 sin theta. So Ni is taken as N1 by N2 into square root of 1 minus cos square theta. Here we have applied the equation or formula like sin square theta plus cos square theta is equal to 1. Now at the point of interface, that is at B point, what happens? Here N1 sin phi is equal to N2 sin 90. Sin phi is equal to N2 by N1 into sin 90. Where sin 90 is 1, apply this value in the above equation, we get sin 90 minus theta is equal to N2 by N1. That is cos theta is equal to N2 by N1. This is our second equation. Substitute the second equation in equation number 1. We get sin I is equal to N1 by N0 square root of 1 minus N2 by N1 square. Here take the LCM value and simplify it. Sin I is equal to 1 divided by N0 square root of N2 square minus N1 square minus N2 square, where sin I is equal to square root of N1 square minus N2 square divided by N0. Here take the inverse value, so we get I is equal to sin inverse of N1 square minus N2 square divided by N0. So take the value sin I, that is I max is equal to sin inverse of square root of N1 squared minus N2 squared, where N0 is taken as 1, that is refractive index of air medium is 1. So numerical aperture, that is NA, determines the light gathering ability of the fiber. It is defined as sine of the acceptance value. That is numerical aperture is equal to sine I max, where NA is equal to sin I max is equal to square root of N1 squared minus N2 squared. In this we have discussed about the acceptance angle of the fiber and numerical aperture of the fiber. Thank you.